You hear the terms neural networks and artificial intelligence thrown around all the time, right? But what is a neural network really? Let's cut through the hype. Today, we're actually going to build one from the ground up, piece by piece, so you can see exactly what's going on under the hood. So, it all boils down to this really big question. How does an AI actually learn to think? You know, how does it go from just a bunch of raw data to making a real prediction, like telling a cat apart from a dog? Well, believe it or not, the answer starts with one surprisingly simple idea.
And that simple idea? It's the neuron. Look, if we're ever going to understand these huge, complicated networks, we've got to start with the most basic building block. It all starts here.
Okay, see this little diagram? This is pretty much the whole concept in a nutshell. Just think of it as a single, tiny decision maker. It takes in a bunch of inputs on the left, we'll call them x1, x2, you get the idea. Then it gives each one of those inputs a certain amount of importance, or a weight, that's the W1, W2. All it does is add them up and check if the grand total is above some cutoff point, some threshold. That's literally it, a simple yes or no decision. So that whole two-step dance, multiplying the inputs by their weights, adding it all up, and then seeing if it passes that threshold, that entire package, that's what we officially call a neuron. It's the fundamental Lego brick of the whole system. All right, so our neuron seems pretty straightforward, right? It takes in some features, it makes a call. Simple enough. But this leads us to what is maybe the most important question in this entire story. Seriously, this is the idea that changed everything. Yeah, where do these input features actually come from? I mean, for our little neuron to do its job, someone has to figure out what good, meaningful features are and feed them to it. But what if we didn't have to do that? What if the machine could figure out the best features all on its own? And right there, that is the breakthrough idea. What if the features were feeding into our main neuron? What if they weren't just raw data? What if they were actually the outputs, the answers, from a whole team of other neurons? And guess what? That is exactly what we're going to do right now. We're going to take that exact concept and visually build this thing out, stacking these little decision makers together. Okay, so let's start with our two main pieces again. Over on the far left, you've got your raw data, the initial inputs. And way over on the far right, there's our final neuron, the one that's going to make the big decision. But look, right now, there's just empty space between them. Nothing's connected. So here's what we do. We're going to slide a brand new layer of neurons right into that empty space. You can think of them like a team of middle managers. Their whole job is to take that raw data, chew on it a bit, and turn it into something way more useful for the final boss neuron waiting on the right. All right, first step. Let's connect our raw data, our x1 through x4, to this new middle layer we just added. Now, each one of these new neurons gets to have a look at all of that initial information. And here's the cool part. We don't just connect one input to one neuron. No. We connect every single input to every single neuron in this new layer. What this does is create this really rich, dense web of connections. And that's what allows the network to start finding all sorts of interesting hidden patterns in the data. So now we're almost there. With one last set of connections, this whole structure we've been building suddenly becomes something really powerful. As soon as we link the output of our new layer to that final neuron, bam, it becomes a true network. And there you have it. Look at that. The outputs from that middle layer, they've now become the inputs for our final neuron. This is it. This is the core idea in action. We're not feeding it the raw, messy data anymore. Instead, we're feeding it this much smarter, refined, processed version of that data. So this thing that we just built together piece by piece, it actually has a name. This is a two-layer feed-forward neural network. This is the classic, the foundational architecture for so much of what follows. So the really important thing here is to get the anatomy down. You've got the input layer, that's just our starting data. You've got the output layer, that's our final decision maker. And then crucially, you have the hidden layer sandwiched in the middle. And why is it called hidden? Because we don't tell it what to do. It learns all on its own to create the absolute best features to help that final layer get the job done. Okay, so now that we've seen the big picture, let's just quickly zoom back in for a second and look at what a modern neuron is like, because it's a little more sophisticated than that simple on or off switch we started with. The inspiration for all this, of course, comes from biology. I mean, these artificial neurons are basically just functions that very, very loosely mimic what's happening in our own brains, taking in signals and then deciding whether or not to fire. So the modern neuron still does two basic things. First, it calculates that weighted sum of its inputs, just like we saw before. But now it also adds something called a bias. You can just think of this as a thumb on the scale. It just makes it a little easier or a little harder for that neuron to fire. Now, the second step is absolutely key. It takes that total sum and passes it through something called an activation function, which is a nonlinear transformation.
You know that old on or off threshold function we started with? That's actually one type of activation function. But today we have a whole toolbox of them, like sigmoid or the super popular one called ReLU. And this nonlinear step, this is where the magic happens. This is what gives the network its real power. It's what allows these layers to learn incredibly complex, curvy, wiggly patterns in the data, stuff that a simple, straight-line model could never, ever hope to capture.
So let's recap. We went from just one neuron to a whole layer of them. We've seen how just one of these hidden layers can learn to see data in a totally new way. And that kind of leaves us with a final, pretty mind-blowing thought. If stacking just a handful of neurons creates this much power, what happens when you stack not one layer, but 100? Or even 1,000 of these layers deep?